Thank you for the introduction, Dirk Uwe, and from my side as well, welcome to my PhD presentation, where we'll talk about the integration of sodium-ion batteries into suitable applications. And one of the reasons why research in Europe is increasingly focusing on sodium-ion batteries is the global dependence of the lithium-ion battery supply chain. And this dependence becomes very clear when we look at the supply chain of electric vehicles. Here you can see the distribution of electric vehicle production from the year 2023, focusing on Europe, the US, and China. And we can see that Europe has a significant share of electric vehicle production. However, China dominates this market. Electric vehicles rely on lithium-ion batteries. And here again, we can see that China dominates the lithium-ion battery production. And lithium-ion batteries in turn rely on lithium. And here we can see the ownership shares in the lithium mining sector. And we can see the US and China have a large share. However, we also have other players in the field that have a large domestic lithium deposit. However, before we can use lithium for lithium-ion batteries, we need to produce battery-grade material. And this happens in the lithium refining step. And here again, you see the same picture. China dominates this section as well. So overall, we can see a clear imbalance. Europe produces a significant share of electric vehicles. However, the batteries, and especially the lithium required to build these batteries, are largely produced by China. And this, of course, exposes Europe to a significant economic and strategic risk. But why do we use lithium for batteries in the first place? Lithium is a very light alkali metal, has a small radius, and a very negative reduction potential. And this means, from a purely electrochemical view, that we can achieve high voltages and also high gravimetric energy density. However, lithium is classified as a critical raw material, and we can see its availability is quite low, with only 20 parts per million in the Earth's crust. So let's have a look at the next alkali metal from the periodic table, sodium. Sodium has different properties. It is larger, it is heavier, and we can also see it has a less negative reduction potential. And this, again, only from an electrochemical point of view, means we have lower cell voltage and also lower gravimetric energy density compared to lithium. However, sodium is highly available in the Earth's crust, and this makes sodium an attractive candidate from a sustainability and also possibly cost perspective. But what about the supply chain issue? And here we can see a world map of the annual sodium production. And we can see that, of course, China also has large annual sodium production, as well as the US. However, we can see that in Europe and especially in Germany, we already produce sodium, especially for the chemical industry, as well as for salt. The point is that sodium is a very vast material, and in principle, it can be used or produced anywhere in the world. So, to summarize, if we aim to reduce the global dependence of the lithium-ion battery supply chain, we must find alternatives to lithium. And sodium might be an attractive candidate from a sustainability, cost, and also supply chain perspective. However, we've seen that sodium has less favorable electrochemical properties, and this limits their replacement to applications where such performance trade-offs are acceptable. And this in particular includes applications where we for once do not need high gravimetric energy density. And I will now present such a use case where we do not need high gravimetric energy density, where all my further analysis are based on. And this is a high-power automotive use case where we have 48-volt batteries that support the propulsion during boosting and recuperation. And here we can see a typical current profile. We have high currents in the charge and discharge direction. And when we now look at the relative charge, we can see that we are always moving in the mid-SOC range. We have low depth of discharges, and we do not have full charges. And from the application, we also know that we have very demanding lifetime requirements of up to 10,000 equivalent full cycles, where one equivalent full cycle equals a full discharge plus a full charge of the battery. In the original application, we use a costly NMC LTO cell with the following properties: capacity of 10.6 ampere hours, an energy density of roughly 80 watt-hours per kilogram, and very good current capabilities, as we can see here. And if we now want to replace the existing system with sodium-ion batteries, we need to account for the lower maturity level of sodium-ion batteries. And this means that when we want to integrate these batteries into such applications, This is associated with high uncertainties when it comes to economical, but especially technical feasibility. And to overcome these hurdles, I aim to address the following questions. How can we speed up the practical deployment of sodium-ion batteries in suitable applications? And I specifically focused on 3 areas and on 3 different levels: cell level, lifetime and degradation analysis, system level, management, and also field level, where we are going to analyze how we can support the field monitoring for an early adoption. So let's start with the lifetime and degradation analysis. Our goal is to understand the lifetime of commercially available sodium-ion batteries to identify the operating conditions that limit their performance. And in the end, we want to see whether we can fulfill with sodium-ion batteries that are already available the lifetime of such applications. And to do this, we conducted an experimental aging study. And here we can see the basic setup. We have a temperature chamber that is operated at 25 degrees Celsius. We have a cycler here on the left for the charge and the discharge of our cells. And we purchased cells that feature a layered oxide cathode and a hard carbon anode. And here again, we can see the characteristics of the cell. We have a capacity of around of 1.2 ampere hours. We see we have a slightly higher energy density and we have acceptable current rates. So now we cycle the cells by alternating reference performance tests and the pure cycling. Let's first have a look at the cycling conditions. Here on the left-hand side, you can see the characteristic voltage curve over SOC. In light blue, you can see the charge curve, and in dark blue, you can see the discharge curve. And we now vary the operation by varying the voltage operation range. So we have 6 different operating conditions where we vary the mean SOC and also the DOD. Whereas we keep temperature and also the current rate constant. And we do voltage-based constant current cycling considering the cell's hysteresis, hence the difference between the charge and the discharge curve. Let's have a closer look at how this works. So we charge our cell with 2C until we reach the upper limit of the charge curve, and then we discharge our cell again with 2C until we reach the lower curve. And this corresponds to the first condition, in this case 10 to 90% SOC. We also have another condition that is in the mid-SOC range, 30 to 50% SOC. And we have also 2 conditions for the lower SOC cycling. Here, 10% to 30%, increasing the depth of discharge 0% to 40%, and also mirroring this for the upper SOC. Here we can see the condition 70 to 90%, and again, increasing the depth of discharge, we have the condition 60% to 100%. And now, for every category, we cycle several cells because of the lower maturity level of the sodium-ion batteries. And we can even see that for the first condition here, we cycle 40 cells because we initially assumed that this was the category with the most aging. So let's have a look at the reference performance test where we want to assess the state of our battery. Here on the left-hand side, you can see the general procedure, the voltage in orange, and the current in purple. And of course, an important aging indicator is the capacity. So first, we fully discharge our cell to measure the capacity. Then we do pulse measurements to analyze the resistance for 3 different SOC levels or voltage levels in discharge and charge direction, and also for different current rates. And last but not least, we can also see that we are conducting so-called quasi-open circuit voltage measurements where we charge and discharge the cell with a very low current. And here on the right-hand side, we can see that we are also performing additional measurements, for example, CT images. We do this for interesting cells, not for all the cells during every RPT, but we do this if we see any irregularities in our electrical data. So now I want to introduce the results of the aging study. On the x-axis, you can see the equivalent for cycles, and on the y-axis, you can see the normalized capacity. The color corresponds to the aging rate, that is the ratio of the capacity loss to the charge throughput. And we can see that the aging tests are well advanced, with some cells having reached more than 8,000 equivalent for cycles. And that is quite remarkable, and such data has not been reported in the literature for sodium-ion batteries yet. And even for graphitic lithium-ion batteries, such a lifetime is very high. On average, we have a capacity loss of 3.5%. However, we can see that for some cells, we experience faster aging. So let's have a look at where, in which condition this happens. I will now include the conditions separately. First, we have the condition 30% to 50%. The shaded area corresponds to the value range because we have several cells within the condition. The thick line corresponds to the mean value. And I can now also include the condition 10% to 90% SOC. We can see we have a higher spread. However, the capacity fade is still very low. And we can also include the conditions for the higher SOC cycling. And we can see again, very low capacity fade. And I can now include also the conditions for the low SOC cycling. And here we can see we have the lowest capacity fade for these conditions. And we can also see that the higher depth of discharge does not have an influence on our capacity loss. We can see, for example, that this purple condition, 10% to 30% SOC, has higher capacity fade, even though the depth of discharge is lower compared to the condition that you can see here in pink. Another important aging indicator is, of course, the resistance. And here you can say the same thing. We see the value ranges and also the mean values. However, we see a different trend. We see that the highest resistance increase is for higher depth of discharges, and for some conditions, especially for the orange condition, we even see a resistance decrease. Generally, we have a linear trend. So, to summarize, we can see that for the different conditions, we have very different aging behavior measured with the help of the capacity and also the resistance. And even within the same condition, we have experienced different aging behavior. And to understand this more, we need to have a look at the aging phenomena happening in a sodium-ion battery. And here you can see a schematic of a sodium-ion battery featuring a hard carbon anode and a layered oxide cathode. And you can see other typical components, the current collectors, the binder, and also the separator. And I will now include different aging phenomena and where they are happening. However, this will not be a fully comprehensive overview because even for lithium-ion batteries, we do not fully understand the aging phenomena happening in a cell, let alone for sodium-ion batteries. However, I will include these and let's focus on the aging of anode and cathode. So on the anode side, we can see the SEI, and aging is mainly driven by the formation, growth, and also breakage of this passivative layer that bounds cyclable sodium. And this growth is especially accelerated due to the repeated sodiation and desodiation in the anode. And this can lead to a so-called breathing of the cell. This can then lead to a particle cracking, as we can see here. And we can also see that this exposes the electrode surface to the electrolyte again, and this can then lead to electrode-electrolyte reactions. Here we can also see that the ICI can break and dissolve. Another important aging phenomena is the so-called sodium plating. This can happen when the anode cannot fully accommodate the sodium, and it's more favorable for the sodium to plate on the surface of our anode. And this, as you can see here, can have dendritic structures. These can then penetrate the separator and lead to short circuits. On the cathode side, we can see a different set of mechanisms. The cathode can undergo structural transformations that can become, especially at high voltages, irreversible. And we can also see that particle cracking can happen here, again, due to the breathing of our electrode. And again, this also exposes the electrode to further electrolyte and can lead to reactions. We can also see that we have transition metal dissolution, so the transition metal atoms can dissolve into the electrolyte and even move to the anode, as we can see here, and form transition metal dendrites. And these, again, can lead to short circuits. So we can see that aging is highly complex and interconnected. And I will now omit aging phenomena that we cannot reliably detect with our only non-invasive degradation analysis. And here you can see the reduced amount. Here again, on the left-hand side, however, we can assign these aging phenomena now to so-called degradation modes that you can see here in the middle. And we have three main degradation modes. Loss of sodium inventory, where we lose cyclable sodium. Loss of active anode material, where we lose electrode capacity, and loss of active cathode material, where we again lose electrode capacity. And we can have loss of active material in two states, in the desodiated state and also in the sodiated state. And for the sodiated state, this means that we lose electrode capacity that was sodiated, so we also lose sodium. And we now want to analyze in which category, which degradation mode is most prominent. And to do this, we leverage a method that is commonly employed for lithium-ion batteries called differential voltage analysis. And here you can see the principle. we can see here the full cell voltage recorded during the reference performance test of our cell. And here you can see the first derivative of the full cell voltage. And we can also see that the first derivative enhances the features from the open circuit voltage. And we can see some bumps and also some peaks here. We now want to assign these peaks to the specific electrodes. And to do this, we rely on a method called half-cell balancing, where we disassemble a pristine cell, extract the material, and then cycle the electrodes separately against sodium. And we then need to shift the resulting open circuit potential curves so that the sum matches the measured full cell voltage. And here you can see the results on the left-hand side for anode OCP and cathode OCP, and on the right-hand side, you can see the first derivatives. And these degradation modes that you can see here on the left now influence the open circuit potentials and therefore the open circuit voltage, which is then in turn visible in our first derivative. And I now want to illustrate this with a simulated loss of 10% loss of active cathode material in the desodiated state. So let's have a look at that. So we have a loss of active cathode material in the desodiated state. This means we're starting here at the 1. And when the cathode is desodiated, this means that our full cell is charged. And this potential that you can see here will not change with degradation. However, here we can see the second point. Here the cathode is sodiated, and now this potential and all other potentials will be reached 10% earlier for a 10% simulated loss of active cathode material. And mathematically speaking, this corresponds to a compression by 10%. And we can see here the anode OCP. This does not change because we only lose active cathode material. And we can see that the full cell voltage does change because our cathode OCP has changed. And because we're still cycling between 1.5 volts and 3.8 volts, we have a capacity loss because our voltage limits are reached earlier. And this capacity loss is visible here in gray. And now let's have a look at how this influences the first derivatives. Here we can see the shift of the first derivative of the cathode, and we can also see that the full cell voltage curve has shifted as well. And when we focus now on the middle part, we can see that the peaks here shift to the upper left. And we now repeated these simulations not only for loss of active cathode material in the desodiated state, but for all other degradation modes, and also continuously for a capacity or degradation of 0% to 20%. Let's have a look at the results. Here we can see the voltage curve in the case of loss of sodium inventory, as well as the first derivatives below. And we can see in blue here, that is the no degradation case. And in dark red, we can see the 20% simulated degradation case. And we can also have a look at the first derivatives, and we can also include the capacity loss that results from a 20% simulated degradation. And again, we can do this for all other degradation modes. And we can see very distinct patterns. We can see, for example, that for loss of active anode material in the desodiated state, this plateau becomes more pronounced with higher simulated degradation. And we can see that this results in a peak shift to upwards. We can also see that this results in a very low capacity loss for the 20% simulated degradation. And we can also see the contrast loss of active cathode material in the sodiated state, where we can see that this plateau is nearly disappearing completely. And this corresponds to a very high capacity rate. So let's continue with the analysis of the peak evolution per degradation mode category. Here we can see again the category loss of sodium inventory, and we can now only focus on the case of no degradation and the 20% degradation. We can identify 5 characteristic peaks: HP1, high point 1 to HP3, and also LP1 to LP2. And we can now analyze how these shifts evolve. And we adopted a visualized approach. And here we also separated the X values from the shift for the Y values. And here you can see we have for the X value the rectangle, and for the Y value we have the circle. And if the circle is purple, this means that we have a shift downward. And if the rectangle is purple, this means we have a shift to the left. And we can repeat this also for low point 1. And as we can see here, low point 1 shifts to the red and also right and also downward. And therefore these colors. And we continue to do this and also for all other degradation modes. And we can see again very distinct patterns, especially when we look at HP3, which has the highest variability over aging. We can see that for loss of active anode material and loss of active cathode material in the desolidated states, this peak shifts upward, and for all other categories, it shifts downward. So we want to compare these theoretical peak shifts now to our real data per cycling category. First, we need to have a look at our data. Here you can see the cycling condition 10% to 90% SOC. We can see here the voltage curves recorded during the reference performance tests and also the first derivatives. And each curve that you see here stems from one reference performance test of one cell within the category. This means for the condition 10% to 90% SOC, we cycle 40 cells, and let's assume we have on average 20 reference performance tests. So here we can see 800 curves. And the color of the curves correspond to the capacity. And again, we do the same thing for all other categories, and we can see, honestly, a less clean picture. And this is because we have different degradation modes overlapping, because we have different aging phenomena overlapping. However, we still want to find out what is the main degradation mode per category. And to analyze this in more detail, we again adopted our visual approach. Here we focus on the first and the last reference performance test, as you can see here on the left-hand side. And we also adopt a frequency-based approach, so we analyze the peak evolution for each cell individually. So this means for HP1, for most of the cells in this cycling category, HP1 shifts to the left. However, we can see that for some cells, it does not change significantly, and for some cells, it even moves to the right. So, and we can also include the circle that represents the DVDQ value, and here we can see for all cells, HP1 shifts downward. And again, we do this for all other peaks and for all other categories. And here you can see the problem or the issue that we have the different aging trends. When we now focus on HP3 in the category 70 to 90% SOC, we can see that only 60% have a clear trend where the shift goes upward, and the other 40%, the peak shifts downward. However, we analyze the agreement between the theoretical peak shift and the peak evolution for each category. And here we only focus on the main degradation modes. And here we can see the results. For the lower SOC cycling condition, where we have the highest capacity fade, we identify as a main degradation mode loss of active anode material in the desolidated state, and we also have indications that loss of sodium inventory is happening. And for the mid-SOC cycling condition, where we have the lowest capacity fade, we identify as a main degradation mode loss of active cathode material, and the same thing for higher SOC cycling, where we, for both categories, also have indications that loss of sodium inventory is happening. However, the question still remains, why do we have such a high, compared to the other cells, capacity fade for the lower SOC cycling condition? And to analyze this further, we took CT images. So here you can see a CT image of our pristine cells, so a cross section. We can see the jelly roll, we can see a mandrel in the middle without a supporting structure, and we can also see the cathode current collector as well as the anode current collector. And now we also took CT image of the cells in the age states across different categories. And here you can see some exemplary cells for the different categories. So here you can see the high SOC cycling, for mid-SOC cycling, and here for low SOC cycling. And for low SOC cycling, we can see that the mandrel is shifted inward, the layers are significantly shifted, and we can see a so-called core collapse. And to understand this better, we need to have a look at the sodium storage mechanism in hard carbon, because our anode is not graphite, it is hard carbon. However, the sodium storage mechanism, or the exact mechanism, is still focus of ongoing research, and we are here using or presenting a model that is highly cited in literature, consisting of two steps. Here on the right-hand side, we can see hard carbon schematic consisting of graphene layers and also a pore. And here on the left-hand side, we can see again our anode open circuit potential curve. And just for your orientation, here the cell is fully discharged. This means that the anode is desodiated. Here the cell is fully charged. That means that our anode is sodiated. Now, let's have a look what happens when we go from a desodiated state to a more sodiated state. We can see that the sodium atoms intercalate into the graphene layers, and this leads in our schematic to a high volumetric expansion. And now when we go to the second step and we sodiate our anode more, we can see that the pores are filled. However, this does not lead to a high volumetric expansion. So we know from our model that we have the highest volume expansion for the first step, for the intercalation. Let's return to the CT images. And here on the left-hand side, you can see a very simplified schematic of the jelly roll. And in the cylindrical cell, two forces are supposed to be in constant equilibrium: the winding force and the expansion force. And if the expansion force now increases beyond the winding force, then the jelly roll will break at its weakest point, which is the mantle. And we can also see that this leads to a shift of the electrode layers, and this can significantly affect our capacity. So let's summarize the first chapter. In this chapter, I presented an experimental aging study of early commercial sodium-ion batteries, and we saw quite a remarkable lifetime behavior, with some cells having reached more than 8,000 equivalent Force cycles, with an average capacity loss of 3.5%. And in total, we can say that this lifetime is very favorable for our high-power application. However, we did some further analysis because we observed very high capacity fade in the lower SOC cycling conditions. And therefore, we did some non-invasive degradation analysis. And we could identify for the problematic cycling conditions that we have loss of active anode material and also loss of sodium inventory as key degradation modes. We also took CT images, and we could see that only for the lower SOC cycling conditions, we had core collapses. And we think this is because of the sodium storage mechanism in hard carbon and the higher expansion for the lower SOC conditions. However, for our application, this is not a major concern because, if you remember, we always cycle in the mid-SOC range. So far, we know that the cells meet the specifications of the applications. However, integrating a new cell chemistry into an existing system always carries risk and can impact the system architecture and therefore the overall cost. So we need to demonstrate that our possibly cheaper sodium-ion batteries do not significantly increase system costs. And one major cost driver is the battery management system. And therefore, in the next part, I will show you how different cell chemistry influence the accuracy and robustness of common BMS estimators, with the central questions being, can we transfer the algorithms that were developed for the origin system to our sodium-ion battery? And also, can we use the same sensor design without compromising estimation accuracy? And because the number of parameter combinations that must be analyzed to answer this question is very large, it is not feasible to investigate this experimentally. And therefore, we adopt a simulation-based approach and introduce a tool that allows us to compare how different cell properties influence measurable signals and also internal states. And as a base for simulation, we need models. And these models are informed by data, as you can see here. We have three different types of data. We have the application requirement data, such as temperature ranges, current ranges, and so on. We have the electrical performance data here as well, and we also have the aging data that was presented earlier. And now, using these data, we can parameterize different models. However, modeling was really not the focus of my work, and I relied on tools from the Institute and also methods from the literature. Using these models, we can now perform battery simulations. And as an output, we get vectors such as current, temperature, and also voltage. We also get the values for the reference states, here in this example, SOC and SOH. And these vectors then go to a sensor emulation stage where we emulate real hardware. And then the output of the sensor emulation stage goes to the algorithm simulation stage, where we have different algorithms and estimators that can also estimate different states. And as an output, again, we get the estimators. And with this framework, we can analyze various sensitivities on the BMS estimator accuracy and robustness. And I now want to illustrate this procedure by assessing SOC estimators. And here you can see the basis of our simulation study. Here on the upper left, we can see the three algorithms that are tested. These algorithms are predefined and are also commonly employed. So we can see the extended Kalman filter and the unscented Kalman filter are both model-based algorithms, and also the Coulomb counter. And now we assess these algorithms for the two cell chemistries, for the original cell, NMC-LTO, and also for the new sodium-ion battery. And we now define different scenarios for different categories. And here the pink categories represent different operation conditions. So we vary the load profiles, we vary the temperature ranges, initial SOCs, and also the aging behavior. We also have categories where we simulate different voltage behaviors and voltage disturbances. And last but not least, we also have a category where we analyze algorithm disturbances, such as faulty initialization. And for every category, we conduct now individual simulations, so several per category, and we only always vary one parameter per simulation to isolate influencing factors. We also have established a base scenario as a source of comparison to analyze how do our algorithms work in favorable to normal states. Here you can see these parameters. And once the scenarios are defined, the simulations are carried out and we get the automatic evaluation of our algorithms per cell. Here you can see again the different categories and you can see the three algorithms here. And each value here is the averaged IA value. And this is the index of agreement. And let me introduce this quickly. Here we can see the basic formula. This agreement is bound from 0 to 1. And let me explain the extrema. The index of agreement equals 1 when our estimated trajectory is a perfect match to our reference trajectory. And the other extremum is when our index of agreement equals 0. And this happens when our estimation trajectory is the complete inverse of our reference trajectory. So let's return to our spider plot. In general, we can see that the average performance is high for all algorithms because in nearly all conditions, we have a very high index of agreement value, so close to 1, which is quite favorable. Let's compare this now to our original cell, NMC-LTO. And here we can see a more diverse pattern, and we can see that especially for the voltage sensor category, we achieve a significantly lower index of agreement value compared to the sodium-ion battery. So let's have a closer look at that. Here you can see the sodium-ion battery for all three algorithms: amp-hour counter, extended Kalman filter, and unscented Kalman filter. You can see here the base values from the base scenario across all three algorithms. And I can now include different voltage disturbances. Here we simulate a gain fault disturbance in the positive and negative direction, and also an offset error in the positive and negative direction. And we can see that the offset errors lead to a low index of agreement. However, overall, the algorithm remains resilient against these offset errors, and we can only see a minimal spread. As we can see, the ampere-hour counter does not change because it is not affected by our voltage disturbances. Now let's compare this to our NMC-LTO cell. And let's focus on the model-based algorithms again. And we can see here that the same scenarios correspond to a significantly lower index of agreement value. And we can also quantify this with our framework. We can see that for the worst case in the EKF, we have a mean absolute error of 1.1%. And for the same scenario for the NMC-LTO cell, we have a mean absolute error of 7%. And this is definitely not acceptable, of course, for the application. To understand this better, we need to have a look at the voltage characteristics. Here on the left-hand side, we can see the voltage characteristics of our sodium-ion battery, and on the right-hand side of our lithium-ion battery. And we can clearly see that there is a difference in voltage range. So our sodium-ion battery has 2.3 volts, whereas our lithium-ion battery only has 1.05 volts. And a higher voltage range leads to a higher observability of our state within our voltage signal. And this is, of course, very favorable for state estimation because a voltage error is not as significant for the sodium-ion battery as it is for the lithium-ion battery. So let's summarize this chapter. In this chapter, I presented a framework for the rapid evaluation and quantification of algorithm behavior to analyze how a new cell technology influences the accuracy and robustness of different estimators. And this toolchain can be used for different algorithms and states. And here I presented an SOC simulation study to benchmark different algorithms for different cell chemistries. And we could see that for our defined scenarios from the high power use case and for the investigated SOC algorithms, we could see that the algorithms can be largely transferable with a very high robustness. We could also see that the voltage characteristics are very favorable for state estimation because we have a high observability of our state of charge in our voltage signal. So we know that we have acceptable lifetime behavior of our sodium-ion cell. We also know that we can manage our sodium-ion cell effectively. However, we now also want to support the integration in the field. And this means we must ensure safe and reliable operation of such batteries. This is particularly important for sodium-ion cells because of their lower maturity level. And this means that we observe different aging behavior, even if the cells are managed effectively. And this variability can create a potential risk of battery failure, and we need to mitigate and detect this early. And for this reason, in the last chapter, I want to present an aging anomaly detection framework that allows us to identify quickly batteries with irregular aging behavior, allowing us to react before a potential failure might occur. However, in this chapter, I will now go back to our original lithium-ion battery system because these batteries are already deployed in the field and we need monitoring measures in place if we now want to replace the existing system. Before I can introduce the aging anomaly detection framework, we need to have a look at the databases because we have worked with time series data. However, now we are working with compressed data. And here you can see the data or the SOH values for an exemplary vehicle over energy throughput. And each value that you can see here stems from one so-called readout. And we can also include other vehicles, and we can even see that these readouts are taken irregularly because they are triggered by the manufacturer or when the customer gets to a workshop. So for each readout, we have a set of variables. We have single values such as SOH, SOC, mileage, and we also have aggregated values, so histogram variables. Here you can see the variable charge temp that describes how much charge is loaded on the cell for a specific temperature range. We also have time temp that describes how much time is spent in a specific temperature range. And last but not least, we have the variable time SOC, where we analyze or which describes how much time is spent in a specific SOC range. And now we not only analyze 3 vehicles, but 600,000 vehicles, as you can see here on the right-hand side. And we can see in general a very diverse aging pattern. However, we can see that the lifetime is also very high, with 6,000 kilowatt hours corresponding to 12,000 equivalent Force cycles. However, even though most batteries exhibit slow aging, as you can see here, we have batteries, especially here in the beginning, that have significantly higher aging. So now let's have a look at the aging anomaly detection framework. So we have data from all over the world, and that is saved in the cloud, as you can see here. And within our data, we do have anomalies, here indicated by the purple points. And now we want to detect these anomalies, and our aging anomaly detection framework consists of 4 subsequent steps. First, the data preprocessing, then the clustering, the statistical modeling, and then in the end, the statistical anomaly detection. And ultimately, we want to identify these anomalies in the field. So let's go through all the steps individually. First, starting with the data cleaning or data preprocessing. Because as you have seen, we have a lot of data and we need to reduce the redundant information of our data. And therefore, we apply principal component analysis. And I now want to show how this is used in the specific case of our data. So let's start easy. We have 2 batteries, and for the 2 batteries, let's focus only on the variable time SOC. And let's assume we only have 2 bits. Time SOC X5, that describes how much time is spent in the SOC region 40 to 50%, and also time SOC X6, describing how much time is spent in the region 50 to 60%. We can now include these values into a coordinate system where on the x-axis is one variable and on the y-axis the other variable. We can even include a third battery, the purple one, and we can see that it has quite a similar behavior compared to the orange one. And now principal component analysis works so that we fit a line in the direction of the maximum variance of our data. And this means that we want to minimize the sum of the squared distances of each point we can see here. And this is the result, principal component 1. And we also see a perpendicular line, principal component 2, that shows in the other direction of the variance. We then rotate the axis, remove the original axis, and then we have our principal components. And just as a reminder, these principal components are now a linear combination of the original 2 variables, time SOC X5 and time SOC X6. And PC1 is the linear combination that explains the maximum variance in our data. However, our use case is more complex. We have for this variable 10 bins, not 2 bins, and we also have 600,000 vehicles, so not only 3 vehicles. And now we apply PCA to all of our data, and we get the resulting so-called loading plot. The loading plot for the time SoC now describes the different contributions of the single variables to our principal component. And we can see that, for example, the highest loading is for when we focus on PC1 for time SoC X6 and time SoC X7. And this makes total sense because these conditions are the most prominent in our use case. And we can now also have a look for all 3 variables at the explaining variance. Here we have all possible principal components on the x-axis and on the y-axis the explaining variance. And we can see that for all aggregated values, we have roughly 80% of explaining variance, which is quite acceptable. We can see that with the principal component 2, we have an additional 20% explaining variance. However, we stick with principal component 1 and have reduced now our histogram variables to 1 principal component variable. This means we can now proceed with the clustering of our cells because we want to account for different load histories. And that's why we adopt a grid-based clustering approach. The first step of our grid-based clustering approach is to determine the cluster variables. And here we do an iterative approach where we then analyze for each variable we cluster by how it affects the cluster sizes and also the spread between cluster sizes. And here you can see the workflow. We see for the green rectangle, we assume we only have 1 cluster and all of our data, so the 12 million data points, are inside of this cluster. And then we cluster by energy throughput for a fixed step size and also by mileage. And we can see that we have the same amount of clusters and we also have the same average values per cluster. However, the spread for mileage is higher than for energy throughput. And we want evenly distributed clusters, and that's why we stick with energy throughput. We continue to compare this with other reasonable variables from our data set, and we always see that our sigma is greater compared to our energy throughput sigma. And therefore, for the first iteration, we stick with energy throughput. And then we repeat the whole procedure for all other variables, and we stop when we do not have a significant change in our cluster sizes and cluster spreads. And this yields 3 cluster variables: energy throughput, PC1 time charge, and PC1 charge temp. The second step is the choice of the step size, so the granularity of our clustering approach. And here we apply a so-called robustness condition, where we say a cluster is robust if the 95% confidence interval of its mean is inside a plus minus 0.5% band. And let me explain visually how this works. Here on the left-hand side, we can see some data points over energy throughput. And let's assume we have a step size that only includes 5 data points. So our n is low and our sigma is high. And now we can calculate the mean plus minus 0.5%, calculate the 95 confidence interval, and we can see that the W is higher than our allowed uncertainty. So this would not be a robust cluster. However, if we now include more data points that are also closer to the mean, we get a different picture. We see that our n is higher and also our sigma is lower. This means that for us, this cluster is robust and we can use this cluster for anomaly detection. We now check for all of the different data points for how many this condition is accepted. And we can see that for a step size that is seen here, we have an acceptance rate of 99%. So we now have our cluster space and different clusters, and we can proceed with the statistical modeling of our clusters. And here you can see on the x-axis the delta SOH values, delta SOH because we need a right skewed distribution of our data. Because we are analyzing aging data, it is naturally left skewed. However, almost most probability density functions are right skewed. And we compare different distribution functions and we assess different goodness of fit statistics. And we saw that for our clusters, the log normal function had the best goodness of fit. And now we have different steps to detect our anomalies. First, we calculate the characteristics of the log normal function for each cluster. We determine the 90% confidence interval, and then we say that we have outliers here in red, for example, when they lie outside of our confidence interval. We also want to validate our data. And we were very lucky that we had prototype data. And this prototype data is visible here in dark green. We can see that for these vehicles, the SOH was consistently underestimated. And now we want to see whether and how much of these data we can detect. Here you can see the resulting clusters. If you can remember, we have a cluster of 300 kilowatt hours. This is why this looks so discrete here. We can now also include the prototype data, as you can see here by the purple circle. We can now use our statistical modeling and our statistical modeling to analyze how many outliers we have detected. Here on the right-hand side, you can see the detection rate in yellow, and we can see that in total we achieve a detection rate of 99%. So to summarize this chapter, we have developed a framework that can provide rapid feedback to manufacturers and cell operators, allowing them to identify and exclude problematic vehicles. And this helps build confidence in a new technology and also enables faster deployment by providing monitoring measures. We validated the methodology based on prototype data, and we achieved a detection rate of 99%. So let's summarize my overall work. So in my work, I have developed and applied experimental, model-based, and also data-based methods for the rapid integration of sodium-ion batteries. In the first chapter, I presented an experimental aging study of early commercial sodium-ion batteries, and we saw quite a remarkable lifetime behavior. We could also see that, especially for the lower SOC region, mechanical degradation might be a problem. However, for our use case, this is not of a very high relevance because we're always cycling in the mid-SOC range where we really have minimal capacity fade. We also know that even the most promising cell is only as effective as our ability to manage it. And therefore, in the second chapter, we analyze how new cell chemistry affects the BMS estimator accuracy and robustness. And we could see that our cell had very favorable characteristics. Last but not least, with the knowledge of good lifetime and algorithm transferability, we then analyze how to support the deployment of novel batteries in our high-power application. For this, we presented an aging anomaly detection framework that allows us to identify problematic vehicles and also support the predictive maintenance strategies of manufacturers or fleet operators. However, there remain open research areas. First, in my dissertation, I solely focus on the non-invasive degradation analysis of the sodium-ion batteries. So we need to conduct postmortem analysis. However, the tests are still running, so we are probably doing this beginning of next year. We are also currently expanding our methods to other cell chemistries of sodium-ion batteries to also analyze how different design parameters and also different cell chemistries affect the aging of sodium-ion batteries. Last but not least, system design. I presented how a new cell technology influences BMS estimators. However, we also need to account for the higher expansion in the low SOC region in the system design, and we also need to have a look at the thermal management of sodium-ion batteries. With this, I have finished, and I'm very happy to answer any questions.